Section 12.7 is triple integrals and spherical coordinates. So now we're extending from cylindrical coordinates to this idea of spherical coordinates. And some things are similar, but some things are a little different. Theta is still the same. So that will be one thing that's fixed. And we're talking about a point, rho, theta, phi, in R3. So three-dimensional space, we're talking about a point in terms of a distance rho, an angle theta, and another angle phi. So rho is the distance from the point that we're talking about in R3 to the origin, to 0, 0, 0. Phi is the angle between the positive x-axis, or z-axis, and the line segment from the origin to the point. We'll see that in a diagram down below. And theta is the standard cylindrical coordinate or polar coordinate angle, theta in the xy plane. It'll range from 0 to 2 pi. We'll note that z should only ever range from 0 to pi, and we'll restrict our attention to only positive values of rho, and we'll find that we can still establish every point in the plane with these restrictions, because when we see where phi points, it starts at an angle of 0 along the positive z-axis. Now if we sweep downward, stop somewhere, we have some angle. This would be greater than pi over 2, what I've just highlighted out, and but it's still less than pi. And the entire way that we'll sweep phi is down to pi. So this covers anywhere we want to point off of that z-axis in terms of an angle phi. Okay, so we see here in the given point, rho, theta, phi. We've got phi highlighted. It's the angle swept down by this blue line, the line segment from the origin to the point, between that line and the z-axis, positive z-axis. Now, the distance from the origin to the point is rho, and that's this component. So we've settled 2 of the 3 components so far, and theta is nice. Theta is just the same value we've dealt with before in polar coordinates or cylindrical coordinates. There's the positive x-axis, and whatever angle is swept out by the projection of this line, it's that red dotted line in the xyz plane. Whatever that projection is, we find the angle theta there, and that's this angle. That's this coordinate. So that's our decomposition of one of these points. Now to set us up to be able to convert from rectangular coordinates to spherical coordinates, let's have a look at some of the trigonometry involved, a little bit more explicit geometry that's going on in here. So we have the same point, rho, theta, phi, drawn more or less in the same place, maybe blown up a little bit so we could see a little bit more closely. So if we think about the fact that this angle theta swept out here is an alternate interior angle with this angle, then we know that this is also phi. The angle at the top of that right triangle is phi as well. If that's the case, then the cosine of phi is the adjacent over the opposite, or the hypotenuse rather, adjacent over hypotenuse. So that means that this z value vertically here is equal to rho times cosine theta once we solve for z. In other words, phi. So cosine phi is equal to z adjacent over rho hypotenuse. So we get our first identity. Z is equal to rho cosine phi, so we can easily translate the z coordinate with that. Okay, going a little further, we look down at this right triangle and the leg on the base that's in the xy plane. Okay, what's in red is in the xy plane. We know that phi, being this angle here, sine of phi is equal to the opposite, this leg, divided by rho. So if we solve for this leg, the red dotted line, then we get rho sine of phi. So now that's that leg of this triangle that's standing up on top of the xy plane right there. Now, we know that this red line is actually representing r in polar coordinates. So that's how we'll translate this a little further back to the xy plane, or back to xyz coordinates. This This is polar coordinates in this XY plane. Okay, so r is rho sine of phi, and that's our substitution. We know how to convert x to r and theta, or vice versa. We know that x equals r cosine theta and y equals r sine theta. So we'll use this new value for r to convert from spherical coordinates into rectangular. And we'll see this on the next page. So we've already got z, and I've restated this identity right here that we have at the top of the page. We've got r equals rho sine of phi. We saw that in the base of the triangle, standing up in the xy plane on the previous page. Now, x equals r cosine theta. That's the old identity from polar coordinates. Since we're in the xy plane, it's perfectly appropriate. We can take that a little further. Since r is sine of phi, we substitute for r here, and we get a full expression, x is equal to rho sine of phi cosine theta. Now we see where these two identities come together. We can do the same thing for y. It's done off to the side, but it's going to look more or less the same. So we have conversions for x, y, and z coming from rho phi theta, or rho theta phi, in our spherical coordinates. Okay, one last identity is to note that rho squared equals x squared plus y squared plus z squared. And of course, we could see that traced out in the previous page if we needed to. Right, we'll move some distance on the z-axis. Moving back to get even with this point. We'll move some distance on the y-axis. We'll move some distance on the z-axis. So that straight line distance rho is equal to the square root of the sum of squares of those distances. So we go back to our work on vector spaces, or three-dimensional spaces and magnitude of vectors there. We'll see the same formula. So those are our relationships linking these. We'll still use our polar coordinate or cylindrical coordinate relationships for r, theta, x, and y, and those will be handy. But otherwise, we have the additional rho and phi to deal with many of these cases. Now, the first example asks us to plot the point given in spherical coordinates and find the rectangular coordinates of the point. So learning our way around this coordinate system, I'll label each of these. Rho is 2, theta is pi over 2, and phi is pi over 2. So our distance from the origin is 2. That's pretty much the last thing to do in plotting one of these. So let's find theta. Theta is pi over 2. So the positive x-axis is here. So we sweep out pi over 2 and we land on the y-axis in the xy plane. Okay, now next, phi is pi over 2 as well. And so phi starts on the z-axis, and we sweep down pi over 2 and also hit the y-axis. So this point is definitely on the y-axis. Now we know that much. We just need to know which distance from the origin to travel, and that's exactly what rho tells us. Rho is 2, so we travel out a distance 2 on the y-axis, and that's our point. 2 comma pi over 2 in spherical coordinates. To find that point in rectangular coordinates, it's just a matter of evaluating this trig expression we have here. X is rho sine of phi cosine theta. Phi is pi over 2, cosine, or theta is pi over 2. Calculate all of these. We get 0 for x, 2 for y, and 0 for z. Using the equations of the boxes above. That's all we've done here off to the side. So we get our rectangular coordinate, x, y, z is 0, 2, 0. Now, a little bit more challenging. We have to be a little bit more careful. We just don't directly plug things into the formula for changing from rectangular to spherical. But we're given a rectangular coordinate here, x, y, and z. And we can start independently in some cases. We don't have to go directly after one thing or another first. Perhaps the easiest thing to find first, though, is rho. And it'll be useful for, well, we'll need to know rho in itself anyway. So rho is the square root of this sum of squares of each of these coordinates, -1 squared plus 1 squared plus negative root 2 squared. That actually comes out to square root of 4, which is 2. So rho is 2. So we've got one of 3 coordinates now. The next thing that might be handy to do is to get a decent sketch of where this point is in R3. So at -1, we traveled away from the page or into the page on the x-axis. We travel to the right, +1 on the y-axis. So what we see now is we're at this point, the red point in the xy plane. And then z is -√2. So we travel down -√2 below the xy plane to find where our point actually is. So it's nice to see that starting from the positive x-axis, we sweep out an angle until we get to quadrant 2 in the xy axis. So we made a note of that. Quadrant 2 in the xy axis, we'll use that information at the very end of calculating theta. But theta is, well, it satisfies the relationship tangent theta equals y over x. So here's tangent theta. Theta is the unknown. It's equal to y of 1 over x, which is -1. That expression is just -1. Tangent of theta equals -1. Technically, using arctangent, that is -π/4. However, -π/4 is not in the second quadrant. So if we add pi to it, we'll swing it around to be at 3π/4. So this is where -π/4 actually is. Positive x-axis, negative y-axis. Okay, add pi to it to land here at the opposite side. So it's 3π/4 for theta. It does take some thinking and recalling a little bit of trigonometry to get through those. Now lastly, we need to find phi. So we use the relation z equals rho cosine phi. We know that z is -√2. We know that rho is 2. So we solve for cosine phi to have this expression. And this one actually works directly with arc cosine. We do have to be careful if we're going to use inverse trig functions that we do wind up picking the correct angle for where we need to be. But this will always work because arc cosine's range is 0 to pi, and that's exactly the values that phi will take on. So phi is equal to 3π/4 in this case. So again, we had matching angles. That's just coincidence. That won't always be the case, but our spherical coordinate is rho theta phi, and that's 2, 3π/4, 3π/4. So those are changing coordinates. Let's take this a little further, and we'll look at evaluating triple integrals with these spherical coordinates. Okay, so the first thing we consider is a spherical wedge. This is a lot like a cylindrical rectangle. A rectangular cylinder piece, or however we defined it in the previous section. So rho theta phi is make up the points of the region E, and they satisfy rho is between A and B. Theta takes on angles between alpha and beta, and phi takes on angles between C and D. Now, this can be a little bit more complicated if we like. We could set this up, we'll see later on that there will be surface bounds for phi, quite possibly. Most of the time, though, when we use spherical coordinates, we will have done so because we've chosen so because we can translate from a more complicated problem to an easier one with usually constants and the limits of integration. So that saves us a lot of work. Well, we divide E into subwedges, E sub I jk, and these subwedges have volume Vijk, or delta Vijk, given by this expression here. Now, where does all that come from? Let's have a look down below at a sketch. So here is our spherical wedge, right? It's a piece of a sphere, more or less. Okay, now the length of this arc is rho d phi from the arc length formula, d phi being the tiny little angle that's been swept from the z-axis downward. Now, rho, so it's the radius rho times the little angle d phi, the infinitesimal angle d phi. Very similar for this arc here, except now our radius along this is actually r d theta, but remember that r is equal to rho sine phi, so r d theta is rho sine phi d theta. So that's getting a little bit mixed up, but we just have to recall what r actually is, because r won't have any part in our integral, so we've converted it to rho and phi. So rho sine phi d theta. And then lastly, an easier one is the thickness of this wedge is given by d rho, a change along the radius from the origin. Now we put all that together. This is our volume element, and integrating over the applying or estimating the sums of the function value within each of these volumes times the volume itself, summing up the triple sum and taking the limit as these volumes shrink to 0, we end up with the integral that we have in the box here. So that the triple integral over the solid E in spherical coordinates can be written as f of rho sine phi cosine theta. That's just x. This expression is just y. That expression is just z. They've all been subbed out because they have to be swapped out to be in terms of rho, theta, and phi. And now part of our integral formula, just like r used to be part of our integral formula, is rho squared sine of phi. Now where does that come from? It's because we had, again, written up here, but it's also seen down here. We multiply all three of these dimensions together, we get rho squared sine phi, d rho, d theta, d phi. Okay, oftentimes d theta and d phi can be swapped in terms of their order of integration, because they'll be integrated with respect to constants, or limits of integration will be constants, but it's not really useful to do it one way or the other. We can just be a little bit more casual about it. So let's apply this formula to a spherical or a triple integral in spherical coordinates. So first, we're asked to integrate the function e to the x squared plus y squared plus z squared, quantity to the 3/2 dv. So that would be a fairly miserable integral to try to evaluate in terms of dx, dy, dz, and get through it carefully. So it's much nicer to convert it. B, they tell us, is the unit ball. The unit ball is the sphere of radius 1. Okay, so to describe the sphere of radius 1 in spherical coordinates, well, rho is the radius of the sphere, so it ranges between 0 and 1. It's all points within this unit ball. We need to sweep out all points in the xy plane in this circular region, 0 to 2 pi. And then we need to sweep from the positive x-axis at phi equals 0 all the way down to the negative z-axis, which is an angle of phi equals pi. Right, so now we have our region. We'll use all of these in our limits of integration once we're ready. One thing to notice is that x squared plus y squared plus z squared is rho squared, raising all that to the 3/2, and we just swap out the inside of that as rho squared, and we end up with the function in the exponent of our integrand is just rho cubed. Okay, so putting all this together, the integral of this function becomes the iterated integral, 0 to pi for phi, 0 to 2 pi for theta, 0 to 1 for rho, our function, e to the rho cubed, and then times part of our integral formula, rho squared sine phi, and then d rho, d theta, d phi. Okay, right off the bat, we integrate with respect to rho. This happens to be a nice u substitution. U equals rho cubed. We can work out the details of it. In fact, we use the u substitution merely to integrate here. A constant of 1/3 appears thanks to it, and otherwise we go right back to rho, and we're evaluating from 0 to 1. So this is 1/3 e to the 1 minus 1/3 e to the 0, or we can factor the 1/3 out of the integral so that we're at 1/3 times the integral, and we have e to the 1 minus e to the 0. E to the 0 is 1, so e minus 1 over 3. Okay, the current integral here is sine of phi d theta d phi. Sine of phi is constant with respect to d theta, so when we integrate with respect to theta, we just have a factor of theta within our integrand, and theta is evaluated from 0 to 2 pi, so this is exactly theta evaluated from 0 to 2 pi. We're just jumping straight to the limits of integration because it's a very simple integral, at least at that point. So we just have a factor of 2 pi that also pushes out to the front of the integral. So we have 2 pi over 3 times e minus 1. And now we're integrating from 0 to pi sine of phi d phi. Antiderivative of sine of phi is negative cosine phi. And apply the limits of integration from 0 to pi. And ultimately we end up with 4 pi over 3 times e minus 1.